The most dangerous assumption in modern autonomy is that everyone shares the same now. Once distance or disruption breaks that assumption, correctness becomes a governance problem, not a networking problem. Start with the hard constraint. No signal, no command, and no correction travels faster than light. When latency is intrinsic, you cannot build a single interactive control loop. You have to build a system where separated nodes act locally, record what they did, and reconcile later. That is what distributed intelligence under light speed delay really means. A lot of leaders hear deep space and think better antennas. Communications hardware matters, and deep space engineering has proven you can build receivers for weak signals and long links. NASA described a next-generation, all-digital deep space network breadboard receiver back in 1993. That work helps you hear and decode messages across extreme distances. But receiver performance does not tell you who is authorized to act, when revocations take effect, or how you audit decisions made during blackout. Bandwidth is not legitimacy. Signal quality is not governance. So the first high-impact finding is a boundary you should enforce in your architecture reviews. Communications modernization and autonomy governance are separate work streams. If you upgrade one without the other, you increase the speed at which you can transmit confusion. The second finding is more counterintuitive. The core technical foundations for asynchronous operation are already mature in pieces. Asynchronous distributed computing has decades of theory and engineering behind it, including delay-insensitive coding and decoder architectures that do not assume synchronized timing. In 1998, researchers presented asynchronous comparison-based decoders for delay-insensitive codes aimed at computation under timing uncertainty. Delay-tolerant networking has also produced models and protocols for intermittent, delayed, and mobility-constrained connectivity. And in 2012, a distributed asynchronous clock synchronization method designed for delay-tolerant networks was published to address coordination when links are disrupted. Yet organizations still design governance as if low latency is normal. That mismatch is where failures hide. The technology can tolerate delay, the institution often cannot. Here's the third and arguably central insight. When nodes receive observations, model updates, and authority changes in different orders, correct behavior becomes ambiguous unless you define invariants that survive reordering. Imagine two remote sites. Both are authorized today. A revocation is issued centrally. One site receives it quickly, the other receives it hours later. Both act correctly according to their local records, and yet the combined outcome can be unacceptable. That is split-brain authority, and it is not a rare edge case. It is a normal outcome of delay. Solving that requires authority protocols that are explicit about time windows, revocation semantics, and reconciliation rules. You need clear answers to questions like, what actions remain valid if a revocation arrives after the action? What gets rolled back? What gets quarantined? And what gets ratified as an emergency exception? Those are policy questions, but they must be made machine legible and enforced in code. That leads to the fourth finding. Audit is not something you add after the fact. Under delay, audit has to be designed as a primary operating mode. The minimum requirement is replayability. After reconnection, you must be able to reconstruct a high-impact decision deterministically from retained logs. That means capturing the actor identity, the authority source, the model version, the data snapshot reference, the local clock state, the key observation, and the reconciliation outcome. Notice what is missing from that list. It does not require you to prove every line of code correct or to fully verify every AI model. Instead, it requires you to prove that the authority system cannot be silently exceeded. A local agent may act, but it must leave an auditable trail that later systems can check against delegated bounds. Formal methods and proof automation are now advanced enough to support this narrower style of assurance. Work on machine-checkable reasoning over structured corpora has progressed, including automated tooling demonstrated in 2023 for working with formalized mathematics. The strategic shift is to verify small protocol surfaces, not make vague claims that the whole system is safe. Prove properties like command validity windows are enforced, quorum thresholds are respected, revocation rules are applied consistently, audit records are complete. The fifth finding is about models, not networks. Many distributed autonomy systems will run different scoring models at different sites for hours, days, or longer. That could be because of bandwidth limits, intermittent links, or deliberate local adaptation. Model divergence is not just an ML problem, it is a governance and liability problem. The practical move is to treat models, feature transforms, policies, and data snapshots as signed, versioned artifacts. Tools like support vector networks, formalized in 1995, and scalable boosted tree systems like XGBoost, published in 2016, show how durable and widely embedded these components become. Once embedded, they will be copied, cached, and modified across the edge. If you do not govern versions explicitly, you will eventually face an incident where nobody can answer a simple question: which model decided this? Version governance must also define rollback boundaries. If reconciliation later shows that one site operated under stale policy, do you reverse actions, compensate outcomes, or change authority rules? Your system needs a pre-committed answer because delay makes after-the-fact debates too slow. The sixth finding is about measurement, and it is where many large deployments fail quietly. Under delay, harmful outcomes can be rare, geographically distributed, and discovered only after reconnection. That means traditional monitoring often has too little statistical power to detect the problem before scale makes it irreversible. Power analysis is not a niche academic exercise here. It becomes operational infrastructure. A flexible power analysis program was published in 2007, and the underlying idea is straightforward. If you cannot detect the failure class you care about, you should not scale the system. For leaders, this becomes a procurement and governance test. Require vendors and internal teams to demonstrate a multi-site blackout scenario. Demand later replay, conflict detection, and bounded rollback. Ask what happens when two sites act under different revocation states. Insist on a metric like what percentage of high-authority autonomous decisions can be replayed deterministically from retained logs. Over the next few decades, these patterns will move from exotic to routine. Critical infrastructure, cloud edge AI, autonomous vehicles, military systems, and space missions will all be pushed toward explicit asynchronous modes. Later, lunar and Mars operations, remote oceanic and polar industry, and other disconnected environments will make delayed policy oversight normal. Over longer horizons, any multi-world institution has to treat delay as a structural condition, not a communications inconvenience. One final implication is worth holding on to. In a delayed world, resilience does not come from faster communication. It comes from bounded local autonomy, durable logs, and rules that still make sense when nobody shares the same present.